Hello everyone, this is Math 111 and we are doing section 4.1 from our book, which is about function inverses. All right, a couple quick definitions. Right, a function f is called the inverse of g, so f is the inverse of g if and only if f of x equals y implies that g of y equals x. For notation, we would say g of x is equal to f inverse of x. This means inverse. Note, this f inverse of x does not mean 1 over f of x. If we wanted to write that, we would write that as f of x, whole thing raised to the negative 1. Right, so where that negative 1 is placed is significantly important. Okay? So essentially, in a function, let's say we have this function, 2, 3, 4, 5, 6, 7, just for fun, 8, 9, there we go. Now this is a function because 2 maps to 3, and 4 maps to 5, 6 maps to 7, and 8 maps to 9. Then the inverse function would simply be going the other direction, right? So 2 maps to 3, 3 maps to 2, switch the x and y's, 5 maps to 4, 7 maps to 6, and 9 maps to 8. So if this is f of x, then this would be f prime of x. Important things to note. Right? If a function is going to have an inverse, it needs to be a well-defined inverse, then it needs to be 1, 2, 1, which essentially means it has to pass both a vertical line test and a horizontal line test. So that one fails, horizontal line test. So it may not have a function, or an inverse, a well-defined inverse. Could have inverses on sections of the graph, but not a well-defined inverse throughout the graph. Both vertical and horizontal line test. Right. So for example, we know that like y equals x squared looks like this. If I want to talk about its function, I'm going to have to limit the domain, or its inverse, y. I'll have to limit its inverse and only look at maybe for x is greater than 0. And then the inverse would be the square root of x and look like this. If I just switch the whole x and y, then it would look like this. And that is clearly not a function because it doesn't pass the vertical line test, right? So we would have to limit its domain here in order for it to have a proper inverse there. Essentially, you switch the x and y's. What's cool is visually, it is do the one that I was just doing, a reflection over the line y equals x. That's pretty cool, right? So this point here is completely reflected to that point there. This distance would be equal to that distance. It's a reflection over the y equals x line. Again, geometrically, that's some pretty cool math. Algebraically, it's pretty fun to solve these. So let's say I have f of x equals 2x plus 8. So in x notation, this would be y equals 2x plus 8. So to find the inverse, I switch the x and y's. So you notice I switch those x and y's, and then I solve for y. So I subtract the 8 from both sides, divide both sides by 2. Y equals 1/2 x minus 4. Take a second, let me graph these for you, and you'll see what happens when they are graphed. So here you see I have the blue line is, so the red dotted line is the y equals x line. The blue line is the f of x, and then the green line is our inverse of x. And if you kind of look at this, like if I were to take, let's look at f of 5, for example, or f, so if I were to go f of 5, let's do one that I have both here. Let's do, so 1, 2, 3, 4, 5. Let's do f of -1 here. I go f of -1 here. Notice this point, -1, 6, is on my graph. If I go over to 6, my inverse, 6, -1, is on the graph of my inverse. So see how it flips? So this one point is -4, 0. Right? So then I would expect this point right here, 0, -4. Right? So you see how they are flipped. Right? So every point that's on one line is going to be on the other line, and of course they cross right at the y equals x line, because that's where they have to cross, because it's a reflection over the y equals x line. So some pretty cool math. All right. If I want to verify a function as an inverse, I don't have to go through the whole process of solving. Let's say they want me to verify that f of x, good grief, f of x equals 3x minus 4, and g of x equals x over 3 plus 4/3. And they want to show that these are inverses. The way that you do that is you take fg of x, and when you plug them together, you better get just x out. So let's find out. F, G, which is that, distribute this in, that cancels with that cancels with that. And that gives me just x left. And then you also have to do it the other way, because it could work one way and not the other way. So now you're going to go gf of x. Everywhere I see an x, I'm going to put my f of x. I just have a common denominator, so I can go ahead and just add the numerators. Cancel, cancel. Cancel, cancel. So these work, and they are inverses of each other. All right. We mentioned that in order for it to have an inverse, it really does need to be a one-to-one function. And let me show you an example where it doesn't. Let's say this is a totally fine, easy-going function. Works out great, right? Because we know this is not a function. All right. 2 can't go to 3 and 4 at the same time, so this is definitely not a function. But if I change that, so My second point, I had 4 going to 3. We didn't have this point. And this is a function. So we can have 2 people going to the same place. We just can't have the same person being in 2 different places at once, right? So this is a function. However, the inverse, if I flip this inverse around, of course it has an inverse, but the inverse is not a function. Should be a 6 there. The inverse would not be a function because when I flip these all around, I have 3 going to 2 and 3 going to 4 at the same time, and that's not doable. That's not okay. All right. I think that should give you a pretty good start on working through your homework.